Electrochemistry is the branch of chemistry responsible for the relationship between electrical and chemical occurrences. Electrochemistry is what allows us to have phones, computers, and virtually anything powered by a battery. To understand electrochem, let's first start by reviewing redox reactions. A redox, or reduction-oxidation reaction, is a reaction in which one reactant is oxidized or loses electrons, and one reactant is reduced or gains electrons. We separate one redox reaction, such as zinc plus copper 2 plus ions, yielding zinc 2 plus ions plus copper, into two half reactions. For this reaction, the half reactions would be copper 2 plus ions plus 2 electrons yielding copper metal, and zinc metal yielding zinc 2 plus ions plus 2 electrons. In this case, the copper reactant loses electrons, or is oxidized, and the zinc reactant gains electrons, or is reduced. In addition, it is important to balance these half reactions so that mass, charge, and number of electrons are equal on both sides of the resultant equation, such that the movement of electrons does not need to be shown in the overall equation. Redox reactions serve as the base of functioning of our electrochemical cell. An electrochemical cell is a device that either generates electrical energy from chemical or redox reactions, or it causes chemical reactions through the introduction of electrical energy. The most basic form of electrochemical cell is the voltaic or galvanic cell. A traditional voltaic cell consists of two vessels, called half cells, that contain a piece of conductive metal or electrode submerged in a solution that contains ions of an electrolyte. The solutions of these half cells are then connected by a material that allows for ion flow called the salt bridge that helps maintain electrical neutrality. The electrodes are then connected together by a wire that allows for electron transfer. When a voltaic cell is allowed to run, the metal electrodes surrounding solution and electrons transmitted on the wire form redox reactions together. At one electrode, oxidation occurs, and the electrode seems to be losing metal mass as it forms ions in solution and releases electrons to the wire. The other electrode accepts these electrons, and they are used to create solid metal on the electrode from the ions in solution via reduction. The electrode that undergoes oxidation is called the anode, and the electrode that undergoes reduction is called the cathode.
We start at the anode, electrons are lost there, and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where? Where? We start at the anode, electrons are lost there, and go through the wire and through the load on fire. They enter the cathode and reduce the cations, and the anions go through the salt bridge back to where?
The other type of electrochemical cell that you need to know about is called the electrolytic cell. While a voltaic cell uses chemical energy to release electrical energy, an electrolytic cell uses applied electrical energy to invoke chemical reactions. An electrolytic cell is also made up of two half cells, but it does not run spontaneously. Instead, an electrical current must be applied to the cell to force the reactions to occur. One example of an electrolytic cell would be how spoons are plated with silver. In this setup, a piece of metal sits in the solution, and when the current is applied, the metal oxidizes and sends its electrons through a wire to the spoon, which then reduces silver ions in the solution of the spoon's half cell to become plated in silver. You don't need to know this extra information for the reagents, but it's important to your understanding of the concepts of electrochemistry. Electron flow or voltage of a voltaic cell is measured comparatively with a standard hydrogen half cell. A standard hydrogen half cell contains two platinum electrodes submerged in equal amounts of 1 molar hydronium ion solution. Because all voltage differences between half cells or cell potentials are measured comparatively, the cell potential of the standard hydrogen half cell is zero. When the type of metal and concentration of the electrolytic solution are varied, the electron flow also varies, because different metals have different tendencies to gain or lose electrons. The tendency for a metal half cell to be reduced is called its reduction potential. Common electrode half cell reduction potentials are listed in reference tables. If one half cell has a greater reduction potential than the half cell that it's paired with, it will undergo reduction, making it the cathode, and the other half cell will be the anode as it undergoes oxidation. Electron flow is from anode to cathode. As such, the total electron flow, or voltage of the cell, is determined by the flow of electrons into the cathode minus the flow of electrons out of the anode. Thus, the voltage of the cell equals the reduction potential of the cathode minus the reduction potential of the anode, where in this equation E represents reduction potentials. Reference table reduction potentials may only be used if the concentration of electrolytic solution is the same in both half cells. Let's look at an example. If one connects a half cell with a copper 2 electrode to a half cell with a gold electrode, a copper half cell has a reduction potential of positive 0.15 volts, and a gold half cell has a reduction potential of positive 1.5 volts. Gold's higher reduction potential indicates that it will be reduced, and copper will be oxidized when the cell is allowed to run. This means that gold is the cathode and copper is the anode in a voltaic cell of these metals. If we assume that they have surrounding solutions of the same molarity, then we know that the voltage of the cell is equal to the reduction potential of gold minus the reduction potential of copper. So the voltage of the cell is equal to 1.50 volts minus 0.15 volts. So 1.35 volts is the total voltage of the cell.